Hello, my name is Ben Hughes. I'm a fourth year mechanical engineering student at BCIT, and this is my astronomy presentation on neutron stars. I'd like to say that unless otherwise indicated, the information for this presentation was gathered from NASA. What are they? Neutron stars are incredibly dense stellar masses that are the remnants of very large stars, which are now approximately 20 kilometers in diameter, but have the mass of 1.4 times our Sun's mass. This would mean that if you could get a sugar cube, approximately 1 cubic centimeter, piece of neutron star material, it would weigh more than 1 billion tons. For comparison, that is 348,432,055.75 2019 Toyota Corollas, or one Mount Everest. How are they formed? When a massive star with a core of 1 to 3 solar masses undergoes gravitational collapse at the end of its life, two things might form depending on the size of the star: a black hole or a neutron star. If it is massive enough, then the force of it collapsing will cause it to implode past its Schwarzschild radius, becoming a black hole. If the star is slightly less massive, then a neutron star is formed. Specifically, a neutron star is formed in the exact same conditions as a black hole, but is prevented from collapsing all the way down to a singularity by neutron degeneracy pressure. While collapsing, the gravitational force squeezing protons and electrons together, forming neutrons, is balanced by the now active neutron degeneracy pressure. Neutron degeneracy pressure occurs when the neutrons are incredibly close together, which causes the very strong outward pressure. This is similar to a white dwarf's electron degeneracy pressure withstanding the collapse of a lower mass star. But the neutron degeneracy pressure is far stronger. The neutron star, with all the neutrons squished together, now forms essentially a hypermassive atom. Types of neutron stars. There's only one thing known as a neutron star, but there are subcategories with differences between them which require defining. They are neutron stars, pulsars, and magnetars. First, neutron stars. Neutron stars are the generic type, probably the most common, but they are very difficult to detect due to the low levels of radiation they emit. It is estimated that there are approximately 1 billion neutron stars in the Milky Way galaxy alone. They are the quiet phase of a neutron star's life after it has had time to cool and spin down. Yet, some neutron stars can also be born as neutron stars and not the faster spinning pulsars. It all depends on how fast the star was spinning before imploding. It is all down to the conservation of angular momentum and the fact that the mass is now much closer to the center. Slight differences in rotation rates between stars pre-collapse could be the difference between forming a regular neutron star or a fast-spinning pulsar. Next, pulsars. Pulsars are the most observed type of neutron star as they emit pulses of radiation at incredibly precise intervals. However, there are also very few of them known compared to regular neutron stars, with only approximately 2,000 known. This is due to the fact that they are emitting radiation in a hard-to-detect gamma wavelength with every rotation, and are rotating with intervals ranging from milliseconds to seconds. Pulsars have very strong magnetic fields, which funnel streams of charged particles out the poles, which in turn produce incredibly powerful emissions of light. These emissions are very focused along the line of emission, and since the pulsar is rotating, the emission sweeps across Earth. This makes it look like the pulsar is turning on and off, or pulsating. However, they are still very difficult to detect due to their emissions primarily being in the gamma portion of the electromagnetic spectrum. As stated, when describing the neutron stars, pulsars will eventually become just regular neutron stars as their rotation energy is lost as electromagnetic radiation. Finally, magnetars. Magnetars have a magnetic field approximately 1,000 times stronger than the neutron stars, which is already trillions of times stronger than Earth's. Due to the construction of magnetars and all neutron stars, the magnetic field is linked with the crust, and if there are any changes in one, it will affect the other. To put the amount of energy locked in the crust-magnetic field relationship into perspective, a magnetar called SGR 1806-20 had a crust quake, and it was estimated that in 1/10 of a second, it released more energy than our sun has in 100,000 years. Why neutron stars matter. Neutron stars matter for a variety of scientific reasons, including observing special relativity, understanding heavy element creation, and understanding effects of hypermagnetic fields on gamma particles. First, observing special relativity. NASA has stated that monitoring the emissions from the extremely fast rotators, known as millisecond pulsars, which have a rotation speed of hundreds to thousands of rotations per second, the Fermi Gamma Ray Space Telescope, or GLAST, has the ability to observe effects due to special relativity, with a NASA scientist, one Alice Harding, saying, quote, "The pulses are so distorted by relativistic effects that we have to filter out all those to figure out what's really happening at the pulsar itself." End quote. This could dispel common understandings of pulsars as lighthouses, as relativistic distortions by the pulsars. Second, heavy element creation. It was commonly believed that heavy elements were created when large stars went supernova by the rapid collapse of the star's material, squeezing elements in the core known to be made in the stars, like iron, to form new heavy elements. Now it is currently believed that the heavier elements are formed by binary neutron stars collision. This process is very difficult for astronomers to observe, and balancing the new evidence provided by the LIGO and Virgo detectors against the abundance of heavy elements in space indicates that neutron stars may not be the sole source of heavy element production, but are confirmed to produce them. Third and finally, effects of hypermagnetic fields on gamma particles. Since pulsars emit strongly in the gamma ray portion of the spectrum and have incredible magnetic fields, the LAT science team from NASA think they can determine, quote, whether pulsars' magnetic fields are strong enough that gamma ray photons packing between 4 to 5 giga-electron volts of energy can transform them into pairs of particles and antiparticles, end quote. In recent years, there have been attempts to measure this. However, due to technical limitations of EGRET, the Energetic Gamma Ray Experiment Telescope, it was not possible to see if there were sharp cutoffs above 4 to 5 giga-electron volts, which would prove the particle and antiparticle hypothesis. With the LAT, the Large Area Telescope, it should have the sensitivity to measure the sharp cutoffs. However, at the time of recording, I could not find the result to see if this was a successful test. Thank you very much, and this has been the presentation by Ben Hughes about neutron stars.